Welcome back, friends. I am continuing from the last lecture, wherein we determined the electric field due to a single charge and due to a dipole, and we discussed that at a length. I went slowly and now I can go fast, because this is scribbling to a case where I have several charges Q1, Q2, Q3, Q4, Q5, Q6, etc. Okay, which are at separations R1P, this point P, R2P, R3P, R4P, R5P, etc. No problem. So they are individual charges, and individually they contribute to the potential at the point P. And because they are individual charges, so I can write the value of V1 as 1 upon 4 pi epsilon naught Q1 upon this, Q2 upon this for V2, and V3, Q3 upon this, etc. etc. And then these Q1, Q2, Q3, etc. could be positive, could be negative, it doesn't matter, and so they contribute positive or negative potentials at that point. So if we want to see as to what is the net potential at that point V, I can write V1 plus V2, and this is the sign of what we can write, and so on. Okay, sign of and see, and just introducing it for you algebraically. Okay, I'll get like this. Okay, I can write 1 upon 4 pi epsilon naught Q1 upon R1, Q2 upon R2P, Q1 upon RNP, etc. Okay, so this is finishes. This is a very simple thing to do. Now, for a continuous charge distribution, normally we talk in terms of what I say dq, dV, this is the volume. Okay, so I am taking the small v because capital V is already for the potential at various points. So dq will become equal to, in the case of volume distribution, rho into dV. In the case of surface distribution, it will be sigma into ds, etc. You know all these things, it's no problem for me. Just now, for example, when I took a shell, okay, and the charge was distributed all over the surface of the sphere, and then the charge density sigma was equal to total charge divided by 4 pi r square, where r is the radius of that shell. And when we considered this in the calculation for the electric field, we found that for any point outside that shell of charge, we had an expression like this. Okay, sorry. Okay, Vr was equal to 1 upon 4 pi epsilon naught Q upon R. Okay, so that was the value of, so I can write this as, instead of this, I will write total charge divided by the total distance. Okay, and when R is greater than capital R, and when R is equal to capital R, then this becomes equal to what I can write as Vr is equal to 1 upon 4 pi epsilon naught Q upon R, which is the value of the potential at the surface of the spherical shell. Well, this is the shell which carries the charge, and if I take the center, then the center is equidistant from all set of small charges dq, and therefore I can say that at the center it will be equal to 1 upon 4 pi epsilon naught Q divided by R. This is what we'll get. Not R squared, this is expression for the electric field. Now, inside this, we argued that the field inside is equal to 0 everywhere, and the field is equal to 0. Then whatever is the potential at center, the same will be the potential anywhere inside, because if we want to move from one point to another point, no work will have to be done for the inner this thing. So anywhere inside, it is equal to 1 upon 4 pi epsilon naught Q upon R. Okay, where R is the radius of, capital R is the radius of that shell. Now, after having done these exercises, I will try to establish as to what is the relation between the electric field and the potential. Before that, I'll tell you what are the equipotential surfaces. And if there are equipotential surfaces, like we have all points within shells inside the shell, if we can take concentric shells, then they are all equipotential surfaces. Similarly, outside also, if we take the concentric spherical Gaussian surface, then everywhere the value of P will be, the value of V will be the same. So these concentric spherical shells which are concentric to the shell under consideration, these will also be equipotential surfaces. Okay, I'll talk to you about that in detail. So the next item is the search of equipotential surfaces. In fact, I told you that inside a sphere, a charged sphere, there is a complete volume which is equipotential. But what matters and what is interesting, what is fascinating is the equipotential surfaces. So, equipotential surfaces, let's take a charge Q, okay, and we find that at a distance r from that charge, the value of the potential is 1 upon 4 pi epsilon naught Q upon R. Okay, Q of course we have already defined, already known to us. R is a value. So for a constant R, V is also equal to constant. That means on all these spherical surfaces that are made over here around this charge, they will be equipotential surfaces. Okay, E oblique S I am writing later. Equipotential surface. Okay. Now let's see. There are two parallel statements. The one is that the electric field at any point P at an equipotential surface is normal to it. Alternately, we can say that for any charge configuration, the equipotential surface is normal to E, that is the electric field at that point. Okay, we can see here, I am just showing you the, we have taken a slice of the sphere, and this is the kind of the electric field point, and you can see anywhere, okay, the electrostatic potential will be the same on a spherical disc. It's very easy to visualize. Now we have a uniform E, electric field, which is going from left to right as you are, and as you look at that, and then we have, these are the uniform electric fields, and then I put a surface over here which I have shown like this, okay, but the surface exactly is normal to the flow of lines of field. So here or here, everywhere, these are equipotential surfaces, and whenever we have any section of these, of course the electric fields have been shown to be uniform, parallel and equidistant lines, as you know from before. So next we see the relation between E and V and define a new unit of electric field, okay, in terms of volts. So volts, and till now I did not define to you that the electric field can have a unit Newton per Coulomb, and now we'll see that it has another unit volt per meter. Okay, so now we go to the next item in the study of electrostatic potential and capacitance, that is about the electric field and the potential and the relation between the two of them. Okay, what we do is we have two equipotential surfaces, okay, which has been shown over here to be almost parallel to each other, okay, and they have the potentials V and V plus delta V. This delta is different from the delta that we do with small delta, okay. Sometimes there is another one, and that is written like this, okay. So we call this Deber, or in flow we call it delta, okay. Anyway, so I'm not concerned with that. Let from the surface A to surface B, let us choose a point so that on the surface B there is a point P, and there passes an electric field which is like this, direction of the electric field. Okay. Now the perpendicular distance from this surface to the point P under consideration is delta L. Okay, distance from A to P, which is located on B, the surface B. So in doing that, let's take, like I have shown here over here in bracket, I have written 1, and 1 is a unit positive charge, which I don't subscribe to. It is a small test charge per unit positive charge. Anyway, but in keeping with what the Sayane say, Sayane means the wise people, the work done will be equal to the magnitude of the electric field multiplied by this charge of unit charge, that will make the force, and force multiplied by delta L. So that will do work done. Okay, delta L. So E, the magnitude multiplied by delta L. And this work done must be equal to, well, I am writing here potential difference multiplied by the, actually it should be rather multiplied by 1. Okay. This is multiplied by 1. You can see that, check. Okay. So I have 1 here multiplied by 1, and that will be basically potential energy difference. Okay, because this is 1 Coulomb. So this is equal to, because VA is equal to V and VB is equal to V plus delta V. So this minus this will give us minus delta V, and therefore we can write the magnitude of the electric field as equal to minus delta V upon delta L, or I can write this as plus the magnitude of delta V divided by delta L. Okay. So what is that? Now, once we obtain this equation like this, I can write with the help of this equation basically, E is equal to minus dV/dl. I can write an expression in general that this will be equal to the electric field, the magnitude of the electric field will be equal to minus dV upon dr into E cap, and also we can call it R cap, because you know, boys and girls, you know that I cannot have a vector quantity here, whether it is vector R or vector R cap. Okay, so there are two things. One is that the electric field is in the direction in which the potential decreases steepest. Okay, the fall of the potential is steepest. And number two, the magnitude of the electric field is given by the change in the magnitude of potential per unit displacement normal to the equipotential surface at the point under consideration. So these are the two features that we have, and if you have understood that, and you must understand that properly, so that we will be using this equation, E is equal to minus dV dr, E will be equal to minus dV dx, E will be minus dV, okay, like that, dV dy, dV dz, but the minus sign should be borne in mind that it's not equal to dV upon dr, it's always equal to minus dV dr. That we'll recall and use that in coming few derivations and explanations. Next we go for the potential energy. Now we are going to deal in the potential energy for a system of charges. I have started with a simple system where I've got two charges, but I will rather start with a system where I have a single charge. All over the universe, there is only that single charge which has no interaction with any other charge, any electric fields, etc., etc. So, if suppose I want to bring it at a certain point P from infinity to that point, then I will require no work to be done. Okay. So that is the argument that I take here in the system of two charges, Q1 at R1 and Q2 at R2 with respect to an origin O, which we can take arbitrarily. So from here to here the radius vector is R1, in here R2, and the radius vector will join two charges Q1 and Q2 is equal to R12, because as you can see that R1 plus R12 is equal to R2, so R12 is equal to R2 minus R1. Okay. There is no problem in that. Now, what we do for this system of charges, I bring Q1 from infinity. As I said, there is nothing else, not even me and you or anything in our imagination. So, if I bring it to a point P, any arbitrarily chosen point P, then there is a potential associated with that. No work done. Work done is equal to 0. So, there is a potential which I can write V1 is equal to 1 upon 4 pi epsilon naught Q1 upon R1P. Okay. But, when you are trying to bring the second charge from infinity to this point under consideration, then there is a problem. And the problem is that because of Q1, the electric field, and when we move this charge Q2, then there has to be a work done. The work done on Q2. And this will be equal to, okay, 1 upon 4 pi epsilon naught Q1 Q2 upon R12. Okay, Q1 Q2 upon R12. So for the system of the two charges, this is only where we have to do the work. We can do the converse. We can first of all bring Q2 and then we can bring later Q1 under the influence of Q2. There also the work done in that case on Q1 will become equal to 1 upon 4 pi, and there is no work done for bringing Q2 over here. This is because the nature of our force that we are encountering is a conservative one. Okay? And of course, we'll use the superposition principle because this value can be positive, this value can be negative. While we do so, what happens that the system has a stored potential energy. And this stored potential energy equal to work done Q2, what we have obtained there, and this is like this. Okay? Because it is an energy, so this should be in joules. Okay, we know that. This value of U will be, for the given system, positive if Q1 into Q2 is more than 0. That is, both are positive or both are negative in that case. And if one of the charges is positive and the other charge is negative, so that Q1, Q2 is less than 0, then this energy will turn out to be negative. Okay. Now next we take another system of 3 charges, Q1, Q2, Q3. Here R12, here R23, here R13, like that. Okay. So naturally what will happen is that suppose I bring in Q1, so no work has to be done. When I bring in Q2, then I have to do the work Q1, Q2 upon R12 multiplied by 1 upon 4 pi epsilon naught. And when we are moving Q3 from infinity to this point, now both of them are active. So there will be Q2, Q3 upon R23 and Q1, Q3 upon R13. If I have a system of 4 charges, then we'll have Q1, Q2 plus Q1, Q3 plus Q1, Q4 divided by these values like that. Whatever is turns over there is the value of R12, R13, R14, etc. And then for Q2 now, which has already been accounted for, there are the charge Q3 and Q4. So Q2, Q3 and then Q2, Q4, etc. And finally I will have Q3, Q4. So that way, even we have a system of n charges, then it should be possible for us to write the potential energy associated with that assembly. And of course, there is one thing, that during the movement of the charges from infinity to that point, okay, the already existing charges should not be disturbed, should not be disturbed, should not be disturbed. So you will ask me that they have an electric field of theirs and they will apply a force, etc. Then again I will say the same thing, that they are held in their positions. How come? I don't know. Only the God knows. Okay? Or what we call Bhagwan Jane, or we call Wallahu alam bis-sawab. And that is where our mind helps us, says go ahead, forget about these silly questions. So you have to forget about such silly questions, okay, and use your brains to obtain the results. The results will be good, very good. So next I go ahead and finally I bring in what is known as the capacitors, their capacities, etc., 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 etc. And of course, I again remind you, please, these are the days where you have questions, so feel free and fearless. Feel free and fearless to ask questions, because you can always ask a question to the one who knows a little bit of science. Okay, he will never shy from trying to answer your questions as much as he or she knows. Okay, I'm only he. Please ask me, I will answer. Right. Thank you very much.